Okay. Thank you everyone for joining today's webinar. Today we welcome one of INT's experts, Jinlang Ouyang. He's a software developer here at INT, and he works primarily with 3D, the GeoToolkit, toolkit. And he's going to talk to us today about how to optimize 3D subsurface web applications. If you have any questions, again, please ask them in the Q&A section. And so we're going to go ahead and get started.
Okay, thank you, Selma, for having me. I will start by introducing myself. My name is Jinlang Ouyang, and I'm a 3D software developer in the GeoToolkit product. But actually, I had used GeoToolkit before I joined INT. 2 years ago, I was still a student on my way to get my master's degree from Rice University. At that time, I did my internship in Subsurface, where I first used GeoToolkit as a framework for building my intern project. So that's kind of the reason why I joined INT after my graduation. It's an exciting experience for me because of the transition from being a user to being a developer for the same product. Now let me briefly introduce GeoToolkit and its 3D module called Connect 3D. GeoToolkit is a comprehensive set of 2D 3D libraries that allows developers to render graphics in their web applications. Connect 3D is a subset of GeoToolkit, and it utilizes WebGL to achieve GPU rendering. In this talk, I want to focus on 3 points. First, the technology behind Connect 3D and how we make the technology easier to use. Second, how simple it is to build and render 3D models using your own data. Last, I want to talk about the optimizations we did for our 3D models. We will also present some examples at the end. I'm sure that people have seen some 3D homepages or applications more or less, but not all people know how 3D rendering works behind the scene. We know that every modern computer has a CPU and a GPU. CPU is responsible for most common tasks, and most of the tasks are simple-threaded. But GPU is mainly used for rendering graphics and, for example, parallel computing. So it's multi-threaded. It's the WebGL technology that allows GPU rendering on web browsers. WebGL, aka Web Graphical Library, is written in JavaScript and a shading language called GLSL. It was first released in 2009, but 3D is hardly said to be common for web applications in the oil and gas industry nowadays. Despite the advantages of 3D rendering and the trend of migrating applications to web browsers, there are various obstacles that developers have to overcome. For example, to get hands on WebGL, a developer must know computer graphics, linear algebra, and 3D math, shaders, and of course JavaScript. If you want your applications to run on different platforms like Windows, Mac OS, or tablet system, you might need to spend extra time on that. Also, there's no good debugger for shading language. That means we cannot just set a breakpoint that we do elsewhere, because the shading language that runs on GPU is parallel. So the steep learning curve, the insufficient cross-platform support, and the difficulty of maintaining make WebGL a beast to work with. I want to give you a more solid idea of 3D rendering. The concept of 3D rendering has a lot in common with photography. If you can look at the slides, we have a screenshot. So we need a camera, a theme, and a light source. They're so essential that we cannot take photos without them. In WebGL, it's the same process, but those equipment are not there for granted. We had to create a camera, a theme, and a light source each time we build an application by playing with the shading language and the low-level graphical APIs. It was a tedious task, so we proposed a solution in Connect 3D. We want our users to have all tools ready when they start to build an application without having to build those tools first. We mentioned that Connect 3D simplifies many WebGL essential elements, but having things encapsulated doesn't mean the users lose control of details, because in Connect 3D, we also provide intuitive interfaces. No matter which framework or programming language the users choose, they can modify and control the rendering settings with minimum efforts. So in the slides, we show that the supported frameworks are Angular, React, Vue, and also Three.js. So Three.js is also a 3D framework. We use that for some basic data types and functions. So in your application, you're free to use that as well. The supported programming languages are JavaScript and TypeScript. As a developer myself, I always have questions when I start to learn new technology. However, sometimes I can get a fast response, but sometimes I can't. If a technology has more users, that means there will be an active community. So it's an active community that developers are looking for when they try out new technologies. Whenever our users have questions about software design or 3D concepts, math, they can always get help by simply opening a support ticket at our community. In our community, the users can also check out the documentations for Connect 3D and also some 3D demos and tutorials. If you go through that, I'm sure you will have a basic idea about how things work in Connect 3D. So far, we have talked about how to get started with Connect 3D and the technology behind it. Now I want to talk about how to build 3D models by simply providing data. Typical EMP features in Connect 3D are weld trajectories, log curves, array logs, seismic surfaces, volumetric rendering, and reservoirs. From the render engine's perspective, it only rasterizes primitives like points, lines, and triangles. For example, if you want to render a simple cube on a screen, it actually consists of 12 triangles. The render engine does not understand those complicated industrial models by default. We want to provide an easier way to render those models so the users can focus on what is more important for them. In the slides, we have three screenshots. The first one is log curves. The second one is surface. And the third one is a CAD model. "3D graphics require a lot of math computations to be done. For example, the render engine needs to perform numerous matrix operations for simple instructions like translating, scaling, and rotation. During our process of developing, we created many help functions that tackle 3D math. Our math module also handles the situation when the users need to trim and fit their dataset. So in the screenshot, the first one is translating. It's the most simple operation in 3D because it's only addition and subtraction. The second screenshot is a matrix multiplication. So when we rotate an object in 3D scene, the render engine actually doing the matrix multiplication like this. In a user's application, models and the features are available and ready to use by providing corresponding datasets. Possible sources for dataset can be local files, cloud storage like AWS, and different services like INTGeo server. So INTGeo server is our internal server that takes care of geophysical data. We also take into account if users have their own data storage. So we provide some data API in our module. So when you check out the documentation for each module, for each 3D models, you will see clearly what kind of data set you should supply. Next, I want to talk about optimization. Why is it important in 3D? So I'm sure all of you have played video games before. In video games, a key factor that affect the player's experience is framework. It's frame rate. So when you see this GIF, you can feel that it's lagging because it only render 8 frames per second. Similar to video games, frame rate plays a significant role in 3D rendering. A stable frame rate gives the user a better experience. When we interact with 3D models, we don't want to feel lagging. And this is why we need optimizations. There are mainly 3 kinds of optimizations in Connect 3D, such as a good software design, an efficient algorithm, and the use of hardware acceleration. A good software design means the architecture of the whole software program is state-of-the-art. The software design determines the upper limit of the performance. If you have a bad design, the performance couldn't be very good. An efficient algorithm and the use of hardware acceleration means we don't do stupid things in our calculation. So let me explain I'm sure that most people know algorithm. It's just math question. So we don't repeat calculations over and over, and we want to find the best way to get the answer. The hardware acceleration is a concept in GPU. So as we have explained, why is GPU faster for rendering graphics than CPU? Because when we render graphics, the GPU can compute faster for basic primitives like a triangle and lines, points. So also it has many built-in functions that are accelerated by the GPU. We want to utilize this and move as much as parallel computations as possible to GPU side. So algorithm and the hardware acceleration determine the lower limit of the performance. Here, I want to use reservoir grid as an example of how we optimize things. For years, web developers in oil and gas industry have worked hard on increasing the capacity of reservoir rendering while maintaining a desirable performance or frame rate. We don't want to, we can render as much as possible cells, but if that means the frame rate is super low, it doesn't work for us. However, due to the limitation of web browsers, it's hard for web applications to catch up with desktop counterpart in terms of performance and scalability. In web application, we use WebGL, but WebGL is kind of a intermediate layer between web browser and GPU. For desktop applications, for example, OpenGL, it's more efficient. So that means we can render more cells on desktop. But we have proposed a solution for this. We want to catch up with the desktop counterpart. Reservoir Grid is a feature in Connect 3D that allows the user to visualize reservoir characterizations. To break down into details, we shall see a reservoir consists of numerous hexahedral cells. Each cell stores information such as property value, IJK index, and custom data. By bonding the cells together, it can display some internal objects like horizons and skeletons. So what makes our reservoir grid stand out if it sounds concise already? The answer is that we rely on all possible hardware accelerations that WebGL is capable of doing. For example, if you see the screenshot, you will see we have all lines for each cell. In the past, we rendered all line as an actual draw call. That means we render the cell first, and we add the outline on top of it. It was slow, so we found a way to do that in shaders. That means those outlines are rendered on the fly, and it does not use extra computing resources. Also, in Reservoir Grid, we have a feature called cell filtering. That means you can filter the cells based on some information like color or IJK index. In the past, we did that in CPU side. So if we want to filtering out some cells, we send the instruction to CPU. We tell the CPU that we don't want to use this part of data. But we found a way that we can impose the same filter on GPU side. So at each frame, GPU does not render those cells. Another optimizations we did is called instance drawing. It's another hardware accelerations for GPU. If you notice that each cell, they may have different shape, but they are hexahedral anyway. So we can utilize instance drawing for that. The above and many other optimizations help our Reservoir Grid render up to 1 million cells with an entry-level GPU. We also have a more advanced version of Reservoir Grid called GigaGrid. In GigaGrid, we use even more optimizations. For example, we introduced a data structure called octree. So we divide the whole Reservoir Grid into many subtrees. That means we can only render the cells that we are able to see. If those cells are behind the surface, we don't render them. Also, in GigaGrid, all cells information are fetched from server. So that means we only get the information, we only get the data if we need it. We don't even have to store them as local files, or we don't even need to transfer them from server to your browser. And if we go back to the camera, to the concept of camera, we can only see the cells that are inside our field of view. That means we don't need to render the cells that are off screen. In GigaGrid, we are able to render like hundreds of millions cells. So in this webinar, we have talked about 3 points. The first is the WebGL technology, and the second is the data set you need to provide it, and for our 3D models. And last, we have talked about the optimizations we did for Reservoir Grid and GigaGrid. If you have any questions or concerns, you can leave it in QA.
Okay, awesome. We're gonna wait a few minutes to see if you have any questions. We did have one already that I answered in the Q&A section. The question was, is the developer community up and running now, and how can I get started? So the developer community is live now, and it's open to licensed users. If you want, you can join at docs.int.com. And like I said, if you have a license, an active license, we'll approve you, and then you have access to online documentation, videos like the one for the webinar today. This will be posted there. Resources like the brochures, training videos, that kind of thing. And also a forum where you can ask any question like, how do I don't have a good question, sorry, but if you have a question about Geo Toolkit, how to code with it, it's a great area for you to ask those kinds of questions. And our developers like Jinlang will be able to answer them in that forum. So yeah, so if you have any questions, just let us know. We're gonna wait just a few minutes. And I wanted to say thank you to Jinlang for doing the webinar for us today. It's really great to have, to hear from our developers directly and be able to kind of open them up to you guys to have, answer any questions, or to really kind of let you guys know what they're doing on the back end to optimize our products in 3D in general for our users. Okay, so we have a question. Can you speak in a bit of detail on how this improves performance in relation to seismic data sets?
Yes, for seismic data set, we work with Blueware, and we use the decompression technology. That means we transfer less less amount of data, and we decompress the data in client side. Also, we have many kinds of version of seismic rendering. The first is local rendering. So we do all the rendering in your own machine. And we also have remote rendering. That means we do the rendering on our server, and we send the generated image to your machine. Another version is WebGL version, and so once we have data, we have the traces, we can send them to GPU, and the GPU will generate the seismic image, and we will be able to show that on your screen.
Okay, great. And then we have another one. I'm asking to clarify how, I think the question is, it's how good do you handle volume rendering for large volumes? And I've asked, just to clarify, are you asking how we handle volume rendering for large volumes, or how efficient we are at that? So let me let them answer that really quick.
So let me get to the screenshot for volumetric rendering. Yeah, that's it.
So maybe answer both questions, Jinlang, like how good are we at handling large volume rendering for large volumes, and then how maybe we go about it.
Okay, so in volume rendering, we have a data format called texture 3D. It's a very efficient data format in WebGL. That means we can have a 3D texture. After we switching to texture 3D, we found that it used much less data, much less amount of data. Although we have many minor optimizations for volume rendering. Actually, I haven't worked on volume rendering for a while. So if you want to know more about volume rendering, you can send us an email, and we will have you answered. We will have your question answered. Yeah.
All right. If there's not any other questions, again, if you'd like the recording of today's session, if you want to email us at marketing@int.com. We'll be sure to send it. We'll also make it available on our website, and give me a day or so to get it posted there. And then it'll also be on the developer community. And that link again is docs.int.com if you want to register there. So great, thank you to our presenter today and everybody who attended, and that concludes our webinar.